All right, we're back. We're going to talk about the second derivative test for extrema. I just realized in saying this that I called the concavity test, which was right here. Oops, come back. Where is it? There it is. Concavity test, the second derivative test. It is different. The way we're going to use them, they're pretty similar. It's not like a big deal, but I just wanted to make sure that I pointed this out. So the stuff we were doing just a minute ago was a test for concavity, determining where it's concave up or concave down. And now we're going to use what's called the second derivative test. Not terribly important what the name is. It's more important that you understand what's going on. Okay, so second derivative test. Go back to the original function on 4,9. My dog just farted, y'all. That was pretty funny. Okay, go back to the original function on 4,9, which is this picture right here. First, look at the point where the function had a relative maximum. That is this point right here. Let me get my pen. Whoops. That is this point right here. Was the graph concave up or concave down at that point? Well, at that point, the graph is concave down, right? Look at the point where the function had a minimum. Well, that is here. Is the graph concave up or down at that point? Well, at that point, it's concave up. This is not necessarily by coincidence. As long as the function is twice differentiable, meaning the first derivative is a smooth curve, think about why that would need to be. As long as the function is twice differentiable, meaning the first derivative is a smooth curve, then we can actually determine whether or not a critical point is a relative maximum or minimum without testing values to the right and the left of that point. We can use the second derivative test. Okay, so this saves us a lot of testing values. We can use the second derivative test. The second derivative test says if f prime of c equals 0, if the first derivative equals 0 at some point, and that makes x equals c a critical point because the derivative equals 0, and if the second derivative is less than 0, then f has a maximum, a local maximum, at x equals c. Okay, that's what happened right here at the top. Maybe I should do that in a different color. That is what happened right here in red. The first derivative was equal to 0 at this point right here. That's getting pretty messy, don't you think? Much better. Okay. So the first derivative, let's look at what was going on here. The first derivative is equal to 0 right here, and the second derivative is less than 0 at that point, as we've already talked about that. If you go back to this page right here, the second derivative from this point right here is less than 0. So when that happens, you have a local maximum at that point. All right, and when f prime of c equals 0 and f double prime is greater than 0, then you have a local minimum. That's what happens right here. Okay, try to keep in mind that what we're doing through all of these graphing exercises, when we graph f prime or f double prime, the first derivative or the second derivative, is we're trying to figure things out about the original function. We're trying to be able to go back to the original function and determine, first of all, if the original function has any maxima, or if the original function has concavity, or if the original function is increasing or decreasing. These are all things that we're trying to determine, and we do that by finding the first or second derivative of the function, okay? And the reason for that is we're going to get really good at graphing an equation without plotting any points, which is really actually pretty nice if you think about it. So we're going to get pretty good at taking a fairly complicated equation and graphing it without actually plotting lots and lots of XY points. Okay, time out. I gotta go let my idiot. Okay, I'm back. All right. So take a second and read this. Primarily, it tells you that we are doing relative maxes and mins, not absolute maxes and mins. In most AP free response questions, they discuss absolute extrema. The reason that you might need these shortcuts, and they are super shortcuts, the reason you might need these shortcuts is because on AP multiple choice questions, often time is of the essence, and these will get you to the answer without actually having to either show all your work or give more detailed answers that you'll need to give on a free response question. Okay, let's see. Okay, let's see. Remember the happy and sad faces? If a critical point happens to occur in an interval where the graph of a function is concave up, then that critical point is a relative minimum. What did that look like with the smiley face? That looked like, oops, oh my goodness. That looked like positive, positive, concave up, right? So then we know that the critical point is a relative minimum because it's down here in the bottom of the concavity, and then vice versa. All right, let's do the last example. Are we on the last? Well, we're almost there. Okay, example 10. Use the second derivative test to identify any relative extrema for the function g of x equals yada, 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 yada. Okay, so we need to find the first and second derivatives. So let's do the first derivative. I'm going to erase my little smiley face over here. Okay, so first derivative, g prime of x equals negative 4x cubed plus 12x squared minus 8x. Okay, we need to find where this we need to find where the first derivative is equal to 0, because go back to the second derivative test. If we can find where the first derivative is equal to 0, and then figure out what the sign is for the second derivative at that point, or on either sides of that point, then we're able to determine the extrema for the function. Okay, relative extrema. All right, so let's factor this or solve it for 0 function here. So equals 0. All right, what can I take out? I can take out a negative 4x. That leaves me with x squared minus 3x plus 2. I think that's right. So I would have x equals 0. Oh, I got ahead of myself there. Okay, so find negative 4x. I need to factor this. I get x, 2, 1. And I believe they're both negative. So back to what I was trying to do a second ago. My zeros are x equals 0, x equals 2, and x equals 1. Okay, so those are the places that I am going to investigate. All right, go back to your second derivative test here. If f prime of c equals 0, which is what we just found, and f double prime of c is less than 0, then f has a maximum, or we can find a minimum as well. So what we need to do is take these points, plug them back in, but where are we plugging them into? Oops, I went the wrong way. We are plugging them into the second derivative. All right, so we found c. That's what we found. We need to plug it into the second derivative. So I need to find the second derivative. So the second derivative is equal to negative 12x squared plus 24x minus 8. Now, we're going to take these values, 0, 2, and 1, and plug them into the second derivative. I don't know if you hear my dog barking, but she's outside going crazy because it's about 20 below tonight. All right, so g double prime of 0 equals negative 8. G double prime of 1, I shall do these in order, is going to be, let's see, that's going to be negative 12 plus 24 minus 8. I think that gives me a positive 4. And then G double prime of 2 is going to give me, let's see, that's negative 12 times 4 plus 48 minus 8. That is negative 48 plus 48 minus 8, which is a negative 8. Okay, so with pretty minimal work here, we are able to determine the relative maxes and mins. Okay, so how would we sum that up? We would say something along the lines of, since G double prime of 0, our first one, is less than 0, there is a relative max at x equals 0. Sorry that the news is so loud in the background. I had it on, I didn't realize it was this loud. And then since G double prime of 1 is greater than 0, there is a relative minimum at x equals 1. And lastly, since G double prime of 2 is less than 0, there is a relative max at x equals 2. Okay, that is it for today. I'm going to let you read this, but we haven't actually done the optimization problems yet. That is the 4.4. Remember I said it officially in our notes fell earlier, but we're going to follow the book and do it at the end. So we might actually even get to 4.4 in class on Wednesday. We might have to do it Friday. I'm debating on Wednesday whether to just do straight through notes and then have Friday as a day of just problems. So we'll see. All right, I'll talk to you guys later. Thanks for listening. Thanks for watching. Bye.